So hello, welcome to the Mechanical Engineering Research Seminar here at South Dakota Mines. So this is Thursday, April 8th. And today we have Sita Syal, who's a PhD candidate in mechanical engineering at Stanford University. And she'll talk about models for sustainable energy systems and issues of equity. She is a National Science Foundation graduate research fellow and has a UDAL scholarship for her research. So she approaches her work from a perspective of human-centered design and has some background. She was got a master's in product design and a design impact program at Stanford, and before that, bachelor's in chemical engineering and energy systems engineering from the University of Michigan. So welcome, Sita. We're glad to have you. I'll turn off my video and hand it over to you.
Okay, fantastic. Thank you so much. Thanks for having me, whether you're here live or watching this at a later time. So, I love to start out without just going straight to the slide sharing to hopefully have a little bit more connection with you all. It's a pleasure for me to be here today, to be able to talk with you. I'm excited to share some of the work that I've been doing and hopefully would love to engage in any questions. And for those watching this a little bit later, please feel free to reach out via email. I'll have my email on the last slide. As Micah mentioned, I got my start in chemical engineering, and then I did this really neat interdisciplinary master's at the University of Michigan in energy systems engineering. And, I wanted to first mention that I spent a lot of my time before graduate school in industry, in the oil and gas industry, particularly, and working in offshore operations on an oil rig in the Gulf of Mexico. And that's really where I transitioned and transformed, shall I say, into a mechanical engineer. So I was dealing with, the ASME codes for bolts and flanges, or how to get that compressor to actually start up. So this talk doesn't address any of that, but I'm sure, hopefully that sort of provides a little bit of connection to you all and really what we as mechanical engineers are dealing with, especially in its breadth. And so at Stanford, I've been able to really scratch the surface and what I think is this kind of new and exciting field being formed at the intersection of engineering, sustainable energy systems, and equity. And so I'll share my screen with you all today to go over some slides, but really I'm really excited to introduce some of these sort of fundamental concepts that I see underpinning this developing field and some of the work that I've done and certainly is ongoing to contribute to this overall goal of equity and sustainable energy systems. So first, I'll start off by telling you a little bit about my personal motivations for this work, and not only this current work, but also what really drives me for my future vision in the next steps. And so really, that driver for me is sustainability. So I'm sure I don't have to convince this group that sustainability is important, that fighting climate change is as complex as it is important. And, I think an area that I think a lot about is how are we going to really this transition of our current energy portfolio to a decarbonized energy portfolio. Now, I don't have to convince you of all of that being so-called important. Where I really want to start this talk is how are we going to make this transition fair without harming individuals in the process? So, I grew up, my extended family is in India, and I grew up going between the US and India very often. And I clearly remember driving down the roads of New Delhi as a kid, passing slum after slum and asking my parents, how do they turn the lights on in their tent? Now, of course, this situation is much more complex than my 8-year-old mind could grasp. But that picture has really stuck with me. And it wasn't until I really started studying engineering at Michigan that I realized I can actually do something about this. So let's zoom out here and take a look at the energy picture we see today and how this sustainable energy transition is currently happening. So what we see is a pretty unequal picture. There are many people who have access to fossil fuels for their energy choices, and they may even bear the burdens from living in proximity to these energy sources. There are people who have access to all types of energy and can choose whatever they like. There are even people who have the choice and the agency to only go with clean sources, like some sort of magical standard that is only available to those who have the means. And then finally, I'd like to make sure to highlight the many, many people throughout the world who have no access to energy at all. Now, this is a bit of a simplistic categorization, but I hope this thought experiment has helped convince you that something is wrong here. There's an unequal distribution of our energy benefits among our population. This can't be a fair distribution. So the concept of fair energy distribution is not new. The movement of energy justice has been around for quite some time now with tireless numbers of advocates. And as you all know, or perhaps have heard, it's really gaining a lot of traction recently, and especially at the highest levels receiving attention. Now, a culmination of the work in energy justice, the energy justice area, really defines this concept in three main areas where you can see sort of boiled, let's say, essentially boiled down to where is the energy being implemented, who's being involved, and are the processes fair? Now, I want to build an energy world that is fair to all individuals, regardless of their backgrounds and situations. Now, the work in energy justice is very motivating and also very qualitative. Difficult for me as an engineer in its current form to integrate into my quantitative work. Here's where I zone in on my work. I seek to embed equity from a human-centered approach in creating new sustainable energy systems models. So not equity at the end, not equity on the side, but from the very beginning and throughout the entire process. Before I move on with the talk, I want to just zone in on two particularly important concepts that I use in my research and I'll use throughout this talk today. So the first is equity. Very easy to say, very difficult to define. In the work I'll present to you today, I'll have this multidimensional framework keep coming up as equity as burdens, benefits, and agency, or the choice that people have over changing those benefits and burdens. For models, I want to give you my take on the classic systems block diagram. So models are more than just their inputs, the black box, and the outputs. I see stakeholder needs, multiple inputs, multiple outputs, multiple model designs as being a key, and the integration between all of them, I should say, as being very key to meaningful models in this space. And the problem frame, as you'll see a little bit later, we'll talk about in some of the work later, this is important to define as the proverbial water that we swim in that affects every choice that we make. So I want to jump into two research examples today. So a project on the solar side, and then some ongoing work in the sustainable mobility area that explores how intentionally prioritizing stakeholder needs and equity can influence the way a problem is not only framed, but then also how models are designed for more equitable outcomes. And so first, I'll talk about this work that was featured in the special issue on socio-technical systems in the Journal of Mechanical Design. I have that paper up on my website, so I definitely invite anyone who's interested to take a look. So this example really focuses on the model building itself and the implications of how all parts of the model interact with each other and glean meaningful conclusions. Let's talk solar. Solar is growing, probably not a surprise to you all, and most of that growth is in the US, particularly in the photovoltaic sector, so the PV sector, as I'll call it, is expected to come from utility scale projects. So exactly what you see in this picture here. Lots of land, lots of modules, lots of sun, one would hope. So it also may come as no surprise that PV costs have come down drastically, which is great news, and thanks to the hard work of researchers working to improve PV technology. Now, what's really interesting and the contradiction comes up is that while these costs are going down, you can see here on this graph with the light blue line coming down significantly in the last decade, still informal interviews I've conducted, things in the literature and surveys have said that solar professionals say that still most of their implementation barriers are financial in nature. I'm sitting here thinking as an engineer, I'm trying to get this technology in the ground. look at the amazing cost reductions we've had on the technology side, what the heck is going on? So this is really the sort of springboard where I got very interested in this area, which led to the project that I'm talking about with you today. Upon further reading and further learning about this area, it comes to fruition that soft costs are really the significant barrier, I should say a significant barrier to implementing these types of projects. So soft costs are the non-technology costs of a solar project. This could include anything from customer acquisition, permitting, things of that nature associated with humans. And you can see in the graph on the side, data from the National Renewable Energy Lab, or NREL, as you may be aware, in Colorado. They find that these soft costs can account for up to 63% of total project costs. These costs are quite variable. They're hard to find data for. They're also often aggregated in the publicly available cost models available to us researchers and engineers. And there's not a lot of publicly available data that is available, and also really understanding what the unsuccessful projects ended up being, right? Most of the data that's available, all of which I've found, is in the successful project space. You'll see this theme come up again later in this part of the talk. And so why is this so hard? Well, soft costs are about people, and people are really hard. So I started thinking about, what could I learn? What could we learn if we re-evaluated how these cost models are being built? What are the inputs that are actually being represented? And what are the stakeholders, who are the stakeholders being represented by this entire modeling process? And could that affect how we understand overall project economics and implementation? And so visually, I thought, can we build a more effective cost model to capture these soft costs? And when I say capture, right, not just the inputs that we're looking at, but also how's the entire system interacting with each other? And so where do I start? True to the human-centered approach, I start with my human-centered approach. So let's start with the stakeholders. If we're going to build a better model, we need to understand these stakeholders at play. This is a visual representation of the informal interviews I did and the analysis of the stakeholders and how they're all connected to each other. I'm going to pull out a couple of learnings. We could probably talk all day about this. So a couple of learnings I want to pull your attention to. Cost models are built from the developer point of view. The developer is the orchestra conductor of all the decisions that go into building a plant. The government agencies, the investors, and the utilities are most likely to benefit from this scenario through taxes, interest, interconnection, things like that, connecting to the grid. The landowners and the local community are the ones most likely to be burdened throughout the procedural steps the developer takes, perhaps through the lack of community engagement in the energy industry, which is a real issue, and the lack of agency to negotiate these land lease rates. Now, this outlook and the language I'm using probably, or hopefully, reminds you of this equity framework that I presented in the beginning. So when analyzing the stakeholders in this intentional way, it shaped the choices that I made for the model, both the inputs and designing the model itself. And so digging into first, like, what is this model actually measuring? So I built this model from a developer point of view, and developers care about how financially viable their project is. Thus, the cost model ultimately calculated the levelized cost of energy. Now, this levelized cost of energy, or LCOE, as it's often referred to, is a measure of cost feasibility. So essentially, it boils down to the total project costs over the lifetime of the facility divided by the total energy generated. This value can be compared to other projects, other energy sources, and it's quite important for investors. So in order to calculate this number, I combined many sources of industry data that further broke these quantities down based on what different stakeholders might be contributing to the overall system. So here's a little bit of what it looked like. This list of inputs was also further disaggregated into a total of 26 sub-inputs based on the data analysis and data availability. And so all of the sub-inputs are not included on this slide, but the inputs here are really backed up by this wide survey of industry data. Each input was also categorized as a soft cost or a technology cost, depending on what the literature had based on what is accepted in the literature. So there are quite a few inputs here. So again, I'd like to point your attention to a couple that are in particular very influenced by my human-centered approach. So first, generally, this development cost and fees is a catch-all term for the soft costs that are usually simplified. I broke this input down into 6 subterms, including things like contingency, profit, permitting costs, labor costs, things of that nature. And then additionally, to better understand how landowners who lease their land for these projects are affected, I disaggregated the land lease costs further to better understand this wide variety of compensation that developers can give. By disaggregating the information, it gives voice to the different stakeholders in the model that is really built from one point of view, the developer. So my next step was then to understand how these inputs and their influence on the output LCOE. And so to do this, I ran a series of sensitivity analyses to quantify this relationship. So equations are great. Let me pictorially represent what's going on in these equations. I first calculated the LCOE at the baseline for all inputs. Then I chose each input one by one and calculated the LCOE with that chosen input at the maximum value, with all other inputs remaining at the baseline. Then I did the same for the minimum. And it's these delta values that I was interested in comparing for each input. So equations are great. I think visualizations are even better. So here's a visualization, a so-called tornado plot, as you may be familiar with, to visualize the range of LCOE values from each input, organized by largest to smallest. So what you're looking at here is that interconnection cost, classified as a soft cost, has the largest range of LCOE. Now, a few observations to note here. My informal interviews with developers yielded that the first thing they think about is when they're developing these types of utility scale projects is where is the grid infrastructure and where is the sunniest location? Both of which we see making the largest influence or difference on the LCOE based on the industry data available. This has so many implications for where these projects are sited. And I came to realize through this analysis, an important implication that is not recognized in this model is who lives near these plants and how are these decisions being made? Sounds a lot like the distributional energy justice concept. Now, my second observation is that you see here that the financial parameters, so to say, appear to change the LCOE the least. This might seem like the inputs are the least maybe important, but when actually comparing them to anecdotes I heard in the interviews, I found that financial parameters actually matter a whole lot for a project moving forward or not. So this model, although built in a with a human-centered approach, built a different way, has no way of knowing if the project fails or not. The data inputs, as I had mentioned before, available to me were from successful projects only, not the unsuccessful projects. So this brings up a whole new dimensionality of importance of soft costs, especially when we're thinking about getting solar off the ground. And so that really ties into the key learnings that I want to share with you to wrap this section up is that, soft costs are really intertwined with the technology costs and how they influence the LCOE. And it's really the quantitative model design and outputs and the qualitative context that gave me the biggest learnings and really, I believe, matter for the solar project planning and energy justice. And then finally, I found that really starting with the stakeholders helped to elevate the stakeholder voices in these very quantitative models and qualitative models as well. And so really open questions that I have, many open questions to pursue. I think we talked about the sunniest places and the grid connected places get prioritized projects. How are we thinking about the communities involved? Can we be modeling the cost to those communities? That's something I'm thinking a lot about right now in the ongoing work I'll present to you right after this. And then finally, the data inputs are inherently biased, right? All data is biased, but what kind of bias are we dealing with here and how are we staying aware of that? Where's the data from the unsuccessful projects? And then finally, I want to bring up this model diagram that you've seen before, and note that where this work was focused is in the inside of that problem frame, right? What are the choices? What are the modeling choices we're making? How do they influence each other? But what I didn't talk a lot about, and what this project wasn't really focused on, what about the problem framing? And so that's a pretty perfect segue into the next project that I'd like to talk with you about. So this is ongoing work in the application area of sustainable mobility. And where I'd really like to focus here is that initial problem framing and how to get that initial problem framing transformed into quantitative model decisions. So I'll take an intentional pause here. I want to shift from the solar world over to the sustainable mobility world. I have some headlines to get us started and make that shift. You may have seen some of these. Really what this is all saying is electric vehicles are coming. California's governor, you may have seen, took some action, kind of following a lot of the countries in Europe, to ban sales of new gasoline cars by 2035. Lots of the major news outlets are really hitting this subject really hard. You could see here with this pretty cool interactive article from the Times. I would highly recommend it. And then finally, our friends at General Motors decided that they would eliminate gas and diesel light duty cars and SUVs by 2035, and other cars are following suit. You'll notice that all of these headlines I'm orienting you to are in the light duty space. So this means passenger vehicles, small trucks, small SUVs. I'll be focusing on this part of the mobility sector for this talk. And I also want to note an assumption I'm making. I assume that light duty vehicles are an important part of the solution to transitioning to sustainable mobility. Now, as you all are definitely aware, this is far from the only solution among the portfolio of solutions that we need to implement. We also need to get people out of cars. We need to expand public transit. We need to rethink our urban planning. The list goes on. But for now, all of the trends and the reality of taking short to midterm climate action lies right outside in our driveways. It turns out that a county by the name of Sonoma County has been thinking about the transition to this electrified fleet for quite some time. So Sonoma County is a small but mighty county of about 500,000 people north of San Francisco with a heterogeneous population. Now, when I said Sonoma County, you may have been thinking of something like this. Or very unfortunately and climate related, you may have been thinking something like this. What you may not know about Sonoma County is that that particular county is very dedicated to equitable climate action. And they have a very entrepreneurial spirit to try new things, especially when it comes to energy. So as a county that's very dependent on light duty vehicles, they came to us with two very interesting questions. So first, how are we going to facilitate this technology transition in a way that won't harm our constituents, our citizens? And second, how in the world are we going to get these conventional vehicles off the road? So the combination of this question really piqued my interest. You know, there's this challenge of combining social, economic, technology issues, and this county is particularly excited to build some sort of engineering-based model, test scenarios, understand how they can make this transition to equitable policies and programs from these model outputs. There's been a lot of work in the EV space, so I thought, sure, no problem, I'll be modeling in no time. Well, if you've been following the theme of this presentation, you may guess that I'm going to say it wasn't actually that easy. Sure, it would be pretty easy for me to make some assumptions, build a few models, give the government our recommendations and move on. But when I worked with my team to really dig into these research areas and try to identify the problem, well, it turned out to be quite a bit more complicated than I thought. I first needed to figure out the frame of our problem as the challenge from shifting to ZEVs, or zero emissions vehicles, and removing ICE vehicles, or internal combustion engine vehicles, from Sonoma County roads. This challenge is very complex, especially when understanding what does it mean to be fair or not cause undue harm. Additionally, looking at this problem through different lenses has implications for people's lives. As an engineering researcher working directly with the local community and with the local government, it's my moral responsibility to ensure that my problem lens is methodically thought through, and then I design models carefully from a human-centered approach and work with the decision makers to appropriately use the outputs in an ethical way. So it's true, there's a vast literature in the transportation space, and that's where I started. So this area where I call clean, light duty vehicle mobility for all, I sort of categorized into three main components. First, there's a lot of work to encourage people to adopt new and increasingly used ZEVs. You may have seen these examples in the literature and in the range of government incentives. You may have even taken advantage of them yourselves to buy electric. There's also emergent work being done, and we saw this in the recent legislation to ban new ICE vehicles sales. Now, members of my research group are actually working on a really neat paper to detail the possible unintended consequences of our California governor's ban on ICE vehicle sales, and what could that mean for the global context. Really interesting. I'm very happy to share that when it's finished with anyone who's interested. So I'm sitting here thinking to myself, I took mass and energy balances when I was an undergrad, and we have a mass balance going on here. We've got new ZEVs coming into the system. We have no new ICE vehicles coming into the system, but Sonoma County's question came up loud and clear. What about the ICE vehicles already in the system? And so this third area, which I'll call decommissioning used ICE vehicles, was missing from many of the discussions. There's some work. You may have seen the famous federal program called, better known as Cash for Clunkers. There's some fantastic work that has been done in the life cycle of that particular program. And it's generally accepted that program did not have the outcomes they had hoped when initially designing it. Additionally, there's fleet turnover models in the literature, specifically for these vehicle fleet turnovers that incorporate cars being taken off the road. But the study is far from complete. What are the effective programs to actually make this happen? And what's the timeline here? Why there's really an assumption baked into everything that the car must be at the very, very, very end of the lifetime before it's removed off the road. Do we have time for that in terms of climate action? Why is that assumption not being challenged? And then finally, I couldn't find pretty much anything about the element of who owns the car that's being removed. Are all ICE vehicles created equal? Who's driving the cars, and what are their personal drivers and needs and characteristics? And how does that affect what cars we're removing and when? So this led me to zone in on my definition for true decommissioning of internal combustion vehicles. So the three main areas of true decommissioning are permanently, quickly, and equitably. So permanently, are these ICE vehicles actually coming off the road? You may think that when you sell your used car to a dealership or to an auctioneer, and if it's at the end of its lifetime, you think it might go to the scrap yards. Well, there's a lot more complications that come up in this particular area, especially when looking at the used car market that we don't know. For instance, the UN did this really fantastic study and found that the US is one of the 3 largest exporters of used vehicles. And typically those vehicles are going to the areas of the world, outside of our borders that have less stringent requirements than we do in terms of emissions and air criteria pollutants. So really, if we're decommissioning, we need to get these cars actually off the road. Now that ties into the second component, quickly. So how fast are these ICE vehicles actually being scrapped? How far into their lifetime? So the Bureau of Transportation Statistics has kept these numbers for a little while. And since 1995, we see that the percentage of vehicles being scrapped in the US has really hovered between maybe 4 and 7%. It's not really going up in any meaningful way. And this number depends on which source you're looking at, but particularly for this source, they're saying the average car lifetime right now in the fleet is almost 17 years. And I'll tell you that number is growing. So people are holding on to their cars. How many more emissions, how many more air criteria pollutants are those cars putting out into the air? Finally, that leads us into the last component of true decommissioning, which is who is benefiting and who is burdening from this transition. And so I'll bring up our familiar framework of equity as a driver for how we wanted to define equity with an eye towards quantification in our models. And so we defined equity as reducing the barriers to accessing benefits to clean mobility. So reducing barriers to accessing the benefits. Let me give you a little visual example of why we chose to focus there in terms of the benefits and barriers to accessing benefits. I'll go to the maps for this one. So what you're looking at here are two maps of Sonoma County. The squiggly lines are the major interstate highways. And on the left side, you're looking at the median annual income in Sonoma County by census tract. Now, and then on the right side, I'll say a statewide program, incentive program, the analysis over the years of where these incentives for battery electric vehicles have gone. This map created by my colleague, Nora Hennessy, she mapped where per capita are these incentives going in terms of Sonoma County census tracts. So really the darker the color, the wealthier the community or the census tract, and the more incentives that are going to that census tract. Now, I do want to make sure in the context of equity to be sure to note that the cost of living in Sonoma County is very different than other parts of the country. So for instance, I'm from Michigan. So just for like a comparison, I looked up, right, that living in Santa Rosa, one of the most populated areas of Sonoma County in the otherwise rural area, is almost 50% higher than Detroit, a big city, as you are all probably familiar with, in my home state of Michigan. And so housing is almost 50% more than some of the actually wealthiest areas in Michigan. So that you can maybe get an example or sort of a reference frame for where these numbers are coming from. I want to focus on the trends here, not necessarily the numbers itself. And so let's actually zone into the Sonoma, sort of Santa Rosa general area to find some patterns here. So what we see here is on the west side of Santa Rosa, we see that there are generally lighter colors, so less wealthy census tracts. And we also see a corresponding less number of incentives per capita going to those census tracts. And then you might guess that on the east side, which is known to be the more wealthy areas, there are a lot darker colors in terms of income. We also see a lot darker colors in terms of more incentives going to those census tracts. And so we saw similar trends when examining the graphs of incentive distribution versus Black or African American populations, Latino populations. And so essentially what this boils down to is that the incentives statewide that the state thinks are equitable for all are actually going to the white wealthy populations. So perhaps the populations that least need those incentives. Now, this gap does not at all explain what it is about the incentives that are not available to those who may need them, or the barriers that these people have to accessing these incentives or other benefits. Additionally, this brings up the question of so many systemic inequities that exist as barriers. So for instance, inequitable urban planning laws that have existed throughout the country have forced communities of color and lower socioeconomic classes to live nearer to the major roadways. This exposes those communities to worse air quality, thus more health effects on average. And so even if they had access to a particular incentive to change their car to electric, they're actually burdened by the choice of the agency that we all make in the cars that we choose to drive. This is really the motivation for further understanding the barriers to accessing benefits when examining clean mobility. And bringing it back to the modeling, this really brings up a lot of questions as well. What are we actually measuring for with these models? So this gets a little complicated. In the last project, you may remember that we had one stakeholder point of view. the developer. So it was fairly straightforward in figuring out what to measure. In this case, there are many stakeholder points of view in the county, all the way from the community choice aggregator, which is instead of the investor-owned utility, to the regional climate protection agency prioritizing greenhouse gas emission declines, the Office of Equity, and then of course, what does the community want? Right? So in this case, there are many different stakeholder points of view in the county that we can take. And the goals and the actions that are taken by those stakeholders may differ from what is manifested in the county itself. And then those model goals will have different outcomes. So you can already start to tell that this is sounding a bit like an optimization problem. And so let me give you a bit of a diagram of where I am today with my fellow research colleagues on building these systems level optimization models for true decommissioning. So on the input side, in addition to the numerical data, I'm in the middle of intentionally building a plan and reaching out, intentionally engaging communities in Sonoma County that have been underrepresented traditionally in decision-making and experience disproportionate burden in mobility choices in that county. Now, this data will help understand the needs, the drivers, and maybe most importantly, the barriers to accessing these benefits like we've seen in the data. From these input data, I am creating these models from different stakeholder points of view. Now, each point of view is calculated in terms of an objective function that may vary slightly between the points of view and may have a different set of constraints. These outcomes will be dependent on the point of view and will elevate the diverse perspectives for the decision makers of the county to center upon when creating more equitable policies and programs. And so this is very much ongoing work right now. We're really excited to see where this goes. And the county partners and the community partners have already been really exciting and fantastic to work with. And so really what I've learned already and where I'm hoping to go is, problem framing matters deeply when building models that include people, technology, and the economics. That's really at the base of what my work is, and trying to understand that interface between qualitative and quantitative model choices. Additionally, when evaluating optimization models from multiple stakeholder points of view, this can lead to different outcomes, which has very different assumptions built in and can lead to different outcomes, lead to different output decisions by the decision maker. And so I'm really curious to understand how those different outcomes will affect those decisions. So to wrap this up, I'd like to just give you a little taste about so many of the exciting things that could be done moving forward, where I'd really like to see this work going as a whole, and where I see this kind of as a vision for this emerging field in engineering. And so I'll throw this slide up here. You may remember this from the very beginning, this with our equity and our model frameworks. And so really where I focus today is on the problem framing and the model decisions. I think there's a lot of fantastic opportunities to expand this work, especially in the types of modeling techniques being used, what points of view are being represented for different types of applications, and an opportunity to better examine and understand the intersectionality of energy systems benefits and burdens. Now, I want to make an impact with this world, and I see an exciting direction focusing on this evaluation and implementation step of these models. So really working across the campus, right? Working with folks in the policy space and the social science space to study how these decisions are being made from seemingly quantitative models. And then finally, sort of on the other side of the spectrum, I also see a huge potential in better understanding how these concepts of energy justice, social justice in general, can influence how engineers make model design decisions, much like a lot of the work that has been done in product design choices and product design decisions. And so how can we understand and most effectively embed these concepts into the front end model design? the last thing I will say is that the true contributions, I think, will not just come from these areas by themselves, but also in how these areas are integrating with each other and influencing each other to bring up new questions that we may not have even thought about under this sort of holistic new way of thinking. And so in all, I see this presentation as scratching the surface of this really new and exciting field right at the intersection of engineering and energy systems and human-centered design and quantitative modeling and data. And I'm really excited to catalyze this with my future team and collaborators. And ultimately, my vision is to make a real impact in the world of engineering as a researcher and educator, and fundamentally shift every part of the process to really embed equity and create in every part to create these technical systems and create a just society. So that's all I have for you today. I'd like to thank you so much for listening to this talk. I also want to specially recognize all the people, my advisors and collaborators, without whom this work would definitely not be possible. And then I'd also like to recognize the National Science Foundation for supporting this work through my graduate fellowship. And that's all I have. So I'd be very happy to take any questions that you might have, and feel free to reach out to me. My email's up on the screen.
Great, thank you, Sita. So there's a couple of people on, and if you have a question, you're welcome to unmute yourself and ask away.
Well, thank you for a very, very nice talk. I do have a question going back to the solar portion of your presentation.
Sure.
And my question is, at one point at the top of a slide, you made a comment about, so where do these installations end up being built?
Mm-hmm.
And and it's interesting you're in California, because that's where I grew up, and so
Cool.
So I grew up in Southern California, and the other half of the California, and when I was a kid, we saw the first wind turbines being put in the Coachella Valley.
Okay.
And then later on, some solar started popping up, and that was mainly city and county governments and businesses. I lived in California a long time ago, but it's when you put that comment in your slide, it got me thinking about all those processes that I saw when I was very active in local politics and local government, when I was in high school and college in California.
Yeah.
And that question about where do these energy conversion facilities end up happening is so politically tied into,
Sure,
and nothing to do with environmental impact or social equity. It's about who's got political power and who's got political clout. And I'm sure you've thought about these things and heard this question before, so how do you, have you thought about, how are we going to integrate all that into the kind of things you're trying to put together?
Yeah, this is such a great question. Thank you so much. I have thought a lot about it. I'm not sure I have a great answer for you. Let's see. So lots of parts to your question that come to my mind initially. So first of all, it's interesting that you bring up this political force, right? As this force that directs decision making. I think about, and I haven't done this in my current work, but I've been thinking a lot about, can that force, or can that be an input, and can that be a stakeholder input? I haven't focused too much. A lot of my work is very community focused, and so I haven't focused too much on understanding the political person here, and what do those relationships between, let's say, the developer and the political decision maker look like, and how does that affect the cost? I think that there could be something really interesting there in how to model that directly in terms of interactions. I haven't done that yet, but I think that it would be a really fantastic direction to go. I will also say that this question of like the decisions that are made because of the political climate and like what the politics are in that particular area, I think that that shows up a lot. I have seen, at least through informal interviews and really trying to understand, some of my work has also been in wind as well, and that issue comes up a lot in wind. A lot of that lies in how the community itself is being engaged, because a lot of the community in these very smaller areas that are potentially being tapped for wind turbines or solar, large scale solar, a lot of the community engagement actually translates into how the political stakeholders are being engaged, because the community and the political scene in the local area are so intertwined. So I also think there's a chance for learnings there with how are in the energy industry, how are we actually changing the way we do things to prioritize community engagement? Right now, I could tell you all the major developers, it's very different in how that's prioritized. Could that actually help further down the line in the project development, these areas of sort of political force, shall we say? So I think a lot about that as well. I guess I'll reiterate, not a great answer to your question, but I think about this a lot and it's really, really interesting. I appreciate you bringing that up.
Yeah, well, thanks for your thoughts. And it's of course, it's a very challenging dynamic to investigate.
Certainly. I think a lot about, as an engineer, I need to get in the heads. I need to understand, walk in the shoes of the political people. And sometimes that's really hard when I'm doing empathy work. So I wonder what that would look like as well. So thank you. Thank you very much for that question.
All right, well, thanks for a great talk. I've got to run. I got to go to another meeting. So thank you so much.
Absolutely. Thanks so much. Here, I guess I can stop sharing and make it a little bit more.
And so we have a couple more minutes for
Okay.
a question or two. I have a couple, but Dan, if you have something top of mind, please go ahead.
Yeah, I love this. This was just great. I'm
Thank
working
you.
with our students on dealing with adaptive challenges, looking at how do we develop the mental capability? How do we look at epistemology, really, to look at this? And of course, you're dealing with that. When you're dealing with the developers and the community, everybody has their own selfish goals, their own selfish objectives.
Yeah.
And so a big part of what we're looking at is then how do we get people to think in these more complex ways? It's not what we think about, and yet your model is really dealing so much with that as well. But it's the adaptive challenge that becomes so interesting, the epistemology, growing the mental, not what we think about, but how we think. And this borders on really what Pierre was getting at as well. Have you looked at this? I mean, I know Stanford researchers are really looking at these issues. Have you dealt with them?
Certainly. Oh, you are bringing up a really, really topic that I'm super interested in. So I'll say that a lot of my work has been on this sort of modeling computational side. And I personally have taken my sort of human-centered design background into the research that I'm doing. Now, taking it a step forward, what I am getting from what you're saying and what you're working in, I think there's been a lot of work that has been done on design, how designers design, right? Like how are designers designing products, designing services, what types of choices are being made? An area that I'm really interested in moving into, which seems very related to what you're bringing up, is how are, essentially I'm sort of the designer of this model. How are these broader thinking concepts in the broader area that are perhaps not right now perceived as engineering, but are so totally ingrained in how we as engineers do work? How do those concepts, embedding those in sort of the front end model design, how does that actually change the quantitative choices that are being made and then the quantitative outputs? Is there some sort of like pathway or sort of causal pathway that we can make? I don't know that answer. I think there's something there, but I haven't done that work. I'll be super upfront, but that's something that's very dear to my heart and where I want to move into after going through that whole process myself. Like, what does that mean for engineers as a whole? I mean, really, I'm sort of I feel like at the PhD level, I'm just thinking about all these like things that I want to do, and I'm in your position, right? And I think that this shift in how are we teaching our engineers to consider exactly what you're saying, these types of out of system ideas and problem frames, does that make better engineered systems? Does that make more efficient systems? Does that make better quantified models? I certainly think so. I'd love to be part of proving that. Does that sort of get at what you were discussing? I get really excited by this, so I should take a breath.
I'd love to follow your work and see how this goes. Right now, I'm working on a seminar with our students to try to get them to do this, and I'm looking at different adaptive challenges. I hope you don't mind if I use the adaptive challenge you bring up here.
Please. Oh, absolutely. I would totally invite you to please follow up with me too, if I can be of any help. I mean, absolutely. That sounds really neat.
Okay, thank you.
Yeah.
And Dr. Dolan works a lot with our Center for Advanced Multidisciplinary Projects, which is students engaged in extracurricular activities, mostly competition teams.
Neat.
Right? So it's outside the bounds of what they're required to learn, and more along the lines of what they want to learn. And so my question was, oh, sorry.
And what we would like them to start learning more on the epistemological side of things.
Yeah.
Which is the tough part of it.
Right.
Yeah,
I mean, to me, yeah.
I was just going to jump in really quick to what you were saying, in case this is helpful for any students that might be listening to this later. That is really exciting to hear, that kind of center, because I will be completely honest, where my interest for this, what is sort of the foundation for my entire doctoral work and wanting to pursue human-centered design to learn more, it actually didn't come from, I had a fantastic education. I loved Michigan very much. I loved chemical engineering. It actually didn't come from my classes. It came from this student experience, like groups. It was sort of an Engineers Without Borders, but it was really dedicated to like human-centered design principles, applying that to engineering and sustainable energy and working with communities. And it was exactly that experience that then years later, when I was in industry and thinking, this is not what I want to do. What do I want to do? That's what essentially brought me back to graduate school, that and the students. But that's really fantastic to hear. That's what's going on in your department, in your school. That's really neat.
Yeah, and some of my questions were along the lines of what has already been addressed, right? Like, it sounds like what are the values that are associated with the algorithm of making these models, and how does that change from different stakeholders or vantage points, right? And so it seems like that's a curiosity, right? I mean, the notion of adding, it's interesting to hear your own story of being a mechanical engineering student and now being a researcher, right? Like, oh, it's something that I could quantify, and maybe the quantification of it isn't enough to understand the complexity of it all, right? And that is generally, like, as we're thinking about having students being more adaptable, being able to solve problems that are beyond what we provide for them in the classroom or behind within the textbook, what is useful. I mean, we have a strong component that is talking about systems engineering throughout our curriculum, and maybe this is an unfair question, but from a systems view, right, and thinking about those models of your own educational experience, right? Like what is something that is missing from what that undergraduate experience is to practice, and then being like meta aware of what those learnings are. Like you've in addition to the things that you've talked about for research, it seems like you've been a teaching assistant or an instructor for a wide range of contexts, right? It was even like teaching design thinking to a religious studies class.
Yeah.
Right.
Yep. That was pretty fun. I'm doing that again. It's in the spring quarter. I'm doing that again actually in a couple of weeks coming up, because it was a hit last year. I think. Okay, so I will say an experience that I felt experience that I had that has always stuck with me in terms of this sort of systems component to maybe the theoretical engineering ABET accredited stuff that I needed to learn, right? As an undergrad, I had this class. So my background is chemical engineering as an undergrad. And I had this class, it was called Separations. Chemies are all about separating things and the infrastructure it takes to separate things. And I just clearly remember that class and that professor had a huge impact on me, not because it was like, okay, I have all this knowledge of like what I'm separating, but he brought in this context of industry and brought in this context of like, who is actually involved in these separations processes? What kinds of infrastructure is needed? I mean, this is like huge infrastructure that then I got to go see when I worked offshore. And it was that perspective that professor brought to me, and that like systems level thinking. I didn't know at the time, but it always stuck with me as this really important experience that I had. And oh, what a great like class that was. And I didn't exactly know why, but I think now with the context I have in pursuing this as a researcher, studying it, I think that's exactly what it was. Like to your point, Micah, it was the systems level approach that was being brought in as equal importance to the engineering and the equations that I was learning. And that integration, that professor clearly was very sneaky at doing this in a really great and exciting way, because I remembered it all these years later. So I think that would be an example of how I did get it was a really important experience for bringing that extra context into the fundamentals that, as an engineer.
Mm-hmm. All right. So we're going to have to wrap this up, but this is one of those things where it's like, oh, it's so interesting and provocative. And right. It's like,
Thanks.
Oh yeah. Right. Like there's a particular context in which you're modeling, right. And it's, solar or transition to electric vehicles. And then it's like, yeah. But the phenomenon is like a bigger systems level thinking that like, you could turn on its head to apply to lots of contexts, even
Absolutely.
one that you're right in the midst of, right? So
absolutely.
So great. So thank you again for your time. I'm going to stop the recording now.
Sounds
and
good.
Thank those that were able to join live and watch this recorded. All right. Thank you.